All right, everybody. Welcome back to another week and another episode of What Did We Learn in Aerodynamics class. So, start things off on, Monday. We are continuing our linearized supersonic flow. All right, still on the topic of linearized supersonic flow. Chapter 12, maybe, in Anderson. And we started with our governing equation, which looks a hell of a lot like our Laplace equation from way back when. Where we define this lambda as the square root of Mach number squared minus 1. Yep. And we went through, again, this is recitation, I'm not going to go through the whole derivation, but we got some useful little tidbits that appear a lot and are pretty cool to know. So we found out for an airfoil, it can be modeled as a flat plate. We have some really easy equations for CL and CD. So CL, lowercase l, can be given as 4 alpha over square root of Mach number squared minus 1, or 4 alpha over lambda. And we got CD as 4 alpha squared over lambda. Yep. And then for a cambered airfoil, we also found slightly different equation where we got CD to be derived as 4 over lambda multiplied by the integral from 0 to d of delta theta c squared dx over c. This is just our normalized chord length, and where theta c is the camber angle. I think that's what it's called, such that this is theta c for a cambered airfoil along its chord line. So those are all useful, particularly these two. You'll see a lot, and they're used quite a bit. This knowledge would have been quite helpful. I think this was an example in class. This relates heavily to question 2 of exam number 2. This would have been quite useful to know, although we specifically asked for something other than linearized supersonic flow theory. But this can be directly related to that problem, and I think that was an example that Professor Herzig gave to you guys in class. All right, then on Thursday we got into a new topic for this course for aerodynamics, which is viscous flow, specifically boundary layer theory. So a boundary layer is, we're going to take some solid object, let's take a flat plate, and we have some uniform incoming flow, U infinity. A boundary layer is a viscous effect in which, due to the no-slip boundary condition, which you guys should be familiar with, there won't be flow at the surface, but there's obviously flow away from the surface. There's going to be, some U infinity. So there is some region in which viscous effects dominate and slow down the flow. So, this region is defined as the boundary layer, and it is defined as given the symbol lowercase delta. And it is defined as the region where the local U U being just the local velocity at that time, is less than 99% of U infinity. So this borderline would be where the local U, this dotted line, is equal to 99% of U infinity. And then after that, we decide that it's arbitrarily, that's the cutoff for the boundary layer. Okay, so we learned a couple different things. One of them being in class that we found was that if you notice the way that let's make that a solid line. If you notice the way that I drew my boundary layer, it's slowly kind of increasing as time goes on, and then there's a transition as Reynolds number crosses some critical Reynolds number where the boundary layer takes quite a big step. And that is the transition from laminar to turbulent. So a turbulent boundary layer is significantly larger than that of a laminar boundary layer. That's because in a if you can imagine, laminar flow, just nice and organized, the only way that momentum can diffuse is directly through streamlines like that. So it has to be, particles rubbing up against each other through viscous effects that then propagates the information upwards around the flow. Turbulent layer, there's more complexity. There's mixing, there's enhanced mixing everywhere. This means that momentum can diffuse, anything can really diffuse quite rapidly in a turbulent system, so that's why the boundary layer is notably bigger. Also, if we are going to look closely, let's say, zoom in some arbitrary section where we have our surface and then the top of our boundary layer. Boundary layers will typically look something like this, where this is our velocity profile, where the velocity is 0 because no slip the wall, and then all the way up to U infinity at the boundary layer. So it's a good, you'll see this diagram all over the place. This is a good idea to kind of have in your head. And let me call this a laminar line, and then turbulence changes things just slightly. There's just kind of a slightly different, tends to be a little bit more aggressive. Turbulence might look something more like that. Just something to kind of be aware of. And then with this, we bring up the discussion of flow separation. So let's say that this is the upper half of some airfoil, so that kind of extends off the page. Our flow will look something like this. But if you know anything about airfoils, you know that as you round this kind of downward camber, the pressure is going to change. And so at certain angles of attack, that pressure can develop what's known as an adverse pressure gradient. So flow in general, you guys should know that, let's say if I define this as the x direction, dp dx, if dp dx is greater than 0, or dp dx is less than 0, two different effects happen. So if flow likes going from, or fluid or anything wants to go from high pressure to low pressure. So it wants dp dx to be negative. It wants the pressure to be decreasing continuously. So if dp dx is less than that of 0, we have a favorable pressure gradient, FPV, or G's. And if it is greater than 0, flow actually wants to go the other way. We have an adverse pressure gradient. But because there's some momentum in the flow, you can have an adverse pressure gradient on an airfoil, but flow still continues because there's still some giant, V infinity pushing this along. But in the presence of an adverse pressure gradient, you're going to slowly lose momentum due to the no-slip boundary condition. So maybe you start to look something like this. And then eventually, you keep going far enough along, or if the adverse pressure gradient is great enough, you're going to get something like this, in which flow actually begins to separate and go backwards. And this is characterized generally on airfoils by stall. So once you have, let's draw an airfoil over here. Once your angle of attack increases to a certain point, you're going to have streamlines going over it. But once we reach stall, there's going to be some separation, and then you have a stalled region. This is when the flow separates now from the body of the airfoil, can no longer continue. So that's generalized as stall, which is caused by an adverse pressure gradient, which is also going to be caused by your boundary layer effects. Okay, so we have a few different definitions of boundary layers. There is a typical boundary layer, a velocity boundary layer, which is what we described earlier, where velocity, it's defined as the cutoff between the local velocity being within 1% of the U infinity, or the overall velocity. There's also the thermal boundary layer, which is the same idea. I didn't write it down here, but it's if you have a thermal gradient across some flow, it's the same thing where if the local temperature is less than that of 99% of the overall temperature, then that you define as within the thermal boundary layer. We also have the displacement thickness boundary layer. So if you have flow over some surface, you can create a boundary layer, but you're also, pretend that line is horizontal, because of the presence of this boundary layer, you're actually going to force some flow upward because there's less momentum here. So that means there's some adjusted streamline that has to go up. It has to be displaced by the existence of the boundary layer. And this height is defined as the displacement boundary layer thickness. We have equations for this. We have equations for this as well. I believe we're going to talk about this later in class. There's a number of different ways of going about things. But the equation that we covered for displacement boundary layer thickness is given as the integral from 0 to y1 being some point in the vertical y direction. Integral 1 minus rho u over rho e u e dy, where E denotes whatever the exterior location is. So, the fact that there's a rho and rho E here means that this can be applied to, compressible flow. Generally, if we're dealing with water, that kind of just falls out. And so in order to solve something like this, you have to understand what U is doing. U is typically a function of Y. We gave the example in class where we talked about quiet flow, where U is given as UE, which is some exterior velocity of Y over D. So that's going to be some linear line like this. So that's just an example. It doesn't apply to every case. And then, so in order to actually execute this integral, you have to figure out what this is, plug it in, do the integral yourself. And then we have another definition of boundary layer, which I believe was just given as theta, which is the momentum boundary layer thickness. And this, I'll cite Anderson for this. So theta is a measure of the decrease in momentum of the flow due to the presence of a boundary layer. So same idea, where these viscous effects are actually going to be taking away momentum from the flow. So theta is just kind of a measure of that. And it's physically what it is. It's the height of the hypothetical stream tube that would be carrying the momentum loss to that. So it's the height of whatever stream tube in which holds as much momentum is lost by the boundary layer. So we have an equation that we went over for this, pretty similar to the last one, is the integral, sorry, my computer just went to sleep, from 0 to y1 of u over ue 1 minus sorry, there's a rho and rho e here. 1 minus u over u e dy. So again, u is typically given as some function of y. You got to figure that out and back that out. All right, so to jump into some homework review, homework 9 is going to be assigned this Thursday and it's due in 1 week. I forget the date, I'm sorry. Some Thursday, I think it's, the week before Thanksgiving break. So questions 1 and 3 are fairly similar. I'm asking you to use linearized supersonic flow to derive a few things. But namely, the most important equations you're going to use are what we derive for CD and CL, which is given as, CL is given as, it's a lowercase l, is given as 4 alpha over the square root of m infinity squared minus 1, and then CD is 4 alpha squared m infinity minus 1. Yep. And so for both these problems, they're fairly similar ideas. I'm asking you to generate some plots, ideally in something like MATLAB. And over some range of something. So I think problem 1, I'm asking you to do it over some range of alpha, and then problem 3, I'm essentially asking you to do it over some range of Mach number. And it's not directly CD and CL, you have to do some manipulations, but I hope you guys will be able to figure those out. And some cool applications of some it's complicated theory, but with simple results, so it's useful, it's cool to know. Problem 2, kind of a little bit of a throwback problem to some stream functions and use some new knowledge that we got over the last few weeks. It is important, so I give you some stream function. It's important to remember our stream function equations. Where u is given as the partial derivative of stream function with respect to x, and v is the partial derivative of the stream function with respect to y. And then once you get what x and y is, you can find some velocity at some point, and I'm asking you to find some functions of the flow, which I hope you guys can do, given what we've learned over the last, I think this covers the last 2 weeks-ish of work. And then, let's see, problem 4 is just some simple work with boundary layers. We didn't cover a whole lot of theory with boundary layers, so I didn't really get into it too much, but I'm asking you to find the displacement and momentum thickness with the equations that I just went over. I won't rewrite them, but you'll have to do some integrals for that. Okay, so with that, that's really all I had for you this recitation. Please let me know if you're struggling with anything during my office hours, 10 a.m. to noon on Wednesdays. Have a good one.